Most people think chocolate is just chocolate. Melt it, mold it, wrap it. But if that were true, then why does one bar snap with a sharp engineered crack while another simply bends and melts? Why has KitKat maintained a crisp architectural crunch for decades, while Cadbury dairy milk remains smooth, soft, and structurally simple? Is it better cocoa, better ingredients, better machinery? Or is something else happening inside that red wrapper? Because here's the truth most consumers never notice. KitKat is not engineered like a traditional chocolate bar. It is built, layer by layer, compressed, bonded, tempered, calibrated. Its crunch isn't an accident of baking. It's controlled material science. And that's why today, inside a real KitKat production facility, we're breaking down the entire industrial process, from wafer sheet formation to lamination engineering to chocolate crystal control to the cooling tunnels that literally lock the snap into place. And by the end of this video, you'll understand exactly why dairy milk cannot replicate this crunch, even if it wanted to. Because the difference isn't flavor, it isn't sweetness, it isn't branding, it's structure. And once you see the internal engineering behind a KitKat bar, you'll never compare chocolate the same way again. Let's step inside the factory.
Before crunch is engineered, ingredients are qualified.
Billions of KitKats begin long before the factory floor. Bulk deliveries arrive. Wheat flour in sealed silos, cocoa mass and cocoa butter in temperature-controlled containers, sugar in granulated bulk storage, milk powder, vegetable fats. Each batch is sampled, moisture content is tested, particle size is analyzed, cocoa butter composition is verified, because variation at this stage creates inconsistency downstream. Production does not begin until raw materials pass laboratory approval.
Crunch starts with compliance.
Chocolate is engineered before it ever meets the wafer.
Cocoa mass is blended with sugar and milk powder. The mixture enters refiners that reduce particle size to below 30 microns. Why? Because texture perception depends on particle fineness. After refining, the chocolate enters conching machines. Large rotating drums mix and aerate the mass for hours. Moisture evaporates, acidity reduces, flavor stabilizes. This is chocolate preparation at industrial scale. Only after this does it move to tempering tanks for controlled crystal formation.
The crunch doesn't begin with chocolate. It begins with fluid behavior.
Flour, water, sugar, and fats are blended into a low viscosity batter. Industrial mixers regulate shear force and mixing time. Too much air incorporation creates fragility. Too little mixing causes uneven spread. The batter must flow uniformly across heated plates measured in millimeters. This stage defines wafer thickness precision.
Thermal control defines brittleness.
The batter is pumped into high-speed wafer ovens. Metal baking plates close under pressure. Heat transfer removes moisture rapidly. Exit moisture levels are measured digitally. The target? Low enough for crispness, high enough to prevent cracking during stacking. Industrial fans cool sheets gradually to avoid stress fractures. The wafer is now structurally stable, but still fragile. Humidity control protects structure. Fresh wafers rest in humidity-controlled chambers. Relative humidity is carefully balanced. Too dry? Sheets become brittle and shatter. Too humid? They soften and lose snap potential. Production pauses here to equalize internal stress. Engineering patience ensures uniform break behavior later.
The adhesive layer is also structural reinforcement.
Imperfect wafers are ground into crumbs. These crumbs blend with prepared chocolate to form a dense internal filling. This paste serves three purposes: bonds wafer layers, distributes mechanical load, enhances chocolate flavor integration. It is not decorative, it is structural adhesive engineering.
Now the architecture is built.
Automated spreaders apply chocolate filling evenly across wafer sheets. Layer 1, chocolate. Layer 2, chocolate. Layer 3. Precision alignment systems ensure perfect stacking. The result is a large composite slab, a multi-layer brittle structure. Unlike a solid chocolate bar, this is engineered heterogeneity.
Air pockets destroy predictability.
The laminated slabs pass through calibrated compression rollers. Pressure eliminates internal voids. Blocks then rest in temperature-controlled rooms. Chocolate partially crystallizes and locks layers together. Structural geometry becomes stable. The snap is taking shape.
Geometry defines fracture lines.
High-speed blades cut slabs into long, narrow bars. Each finger must be uniform in width and height. Laser sensors verify dimensions because break symmetry depends on structural symmetry. Irregular cuts create weak fractures. Precision ensures clean snapping.
This is where the shell becomes mechanical reinforcement.
Prepared chocolate is tempered through heating and cooling cycles. Only stable crystal forms are allowed to develop. The wafer fingers travel through a flowing chocolate curtain. Excess chocolate is vibrated off. Air knives clean the underside. Coating thickness is measured in millimeters. The shell unifies the layered interior into a single engineered bar.
The snap is permanently programmed here.
Bars move through staged cooling tunnels. Temperature gradually decreases. Humidity is regulated. Improper cooling causes fat bloom or weak shell bonding. Proper cooling locks cocoa butter crystals into stable form. The bar is now mechanically complete.
Protection preserves crunch.
Bars enter high-speed flow wrapping machines. Moisture-resistant film seals each unit. Batch codes are printed. Vision systems check alignment and wrapper integrity. Robotic arms group bars into cartons. Cartons are palletized and scanned for distribution. From raw flour to retail shelf, the production cycle is complete. Now we return to the question from the beginning. Why can't dairy milk replicate this crunch? Because dairy milk is a homogeneous chocolate mass. It has no internal wafer lattice, no bonded composite layers, no alternating brittle and tempered structures. It is designed to melt smoothly. KitKat is designed to fracture predictably. Its crunch comes from layered wafer geometry, chocolate adhesive bonding, controlled compression, tempered crystal stabilization, and engineered fracture lines. This is structural architecture, not superior chocolate, not secret ingredients, architecture. That's why one bends and the other snaps. Next time you break a KitKat, you won't just hear a snap. You'll recognize layered wafer engineering, compression physics, and crystal control working together in one precise moment.
If you want more real factory breakdowns, raw materials to final product, explained through engineering, not marketing, subscribe and turn on the bell icon.
Because once you understand how products are built, you start seeing design everywhere.